Today we're going to talk about some more problems involving energy, work, and power. So we're now in the realm of physics. And here's a good example in this particular area. Let's read it together. It says a block of 20 kilograms is pushed against a horizontal spring of spring constant K equals 1200 newtons per meter, compressing the spring 50 centimeters. After being released, the block slides 5 meters over horizontal surface with coefficient of friction K equals 0.2 before reaching a frictionless incline of 30 degrees. How far up the incline will the block slide? Wow, that's quite a problem. And without a good technique here, without a good strategy, you may have a lot of trouble figuring out how to do this. But before we get onto the strategy, let's first make a picture of what's really going on, and then I'll show you what technique will really work for a problem like this. So let's say we have a horizontal surface, we have a spring, we have a block that's being pushed against the spring, and the mass of the block is equal to 20 kilograms. The spring constant K is equal to 1200 newtons per meter. And let's assume that this is the compressed state of the spring, that the spring had been compressed a distance of 50 centimeters. So we have stored energy into the spring by pushing the spring together. Then when we let go, the block will slide over the horizontal surface over a distance of 5 meters. So this distance here is 5 meters. The coefficient of friction is 0.20. And after that, the block begins to slide up the incline. So after some while, the block will be sliding up an incline. At some point, it will reach a certain distance d. And let me use a small d for that. So small d. And we want to know how far it is. So how far up the incline will the block slide? All right, the best technique for that is to use our equation, where we say that the energy initially, any work put into the system, plus any kinetic energy the system has, plus any potential energy the system has, equals the potential energy at the end, final, plus the kinetic energy at the end, plus any heat loss to overcome friction, or wind resistance, or any other resistive forces. All right, so that should be a familiar equation if you've seen videos like this before. Now, let's figure out what we have here. So after we compress the block and we let go, the block will then begin to slide. So there's no additional work input. It's true that we have to do work to compress the spring, but if we start the problem at the moment the spring is compressed and we let go, there's no work input, so we call that equal to 0. All that work input is now in terms of initial potential energy the system will have. Since at the moment we let the block go, nothing is moving, there's therefore no initial kinetic energy, there's only initial potential energy which is stored within the spring, and the equation for that is 1/2 kx squared, k being the spring constant, and x being the distance that the spring was compressed. That equals the final potential energy of the system. Now, if the block slides up a certain distance, like so, and this is the final position, we then know that the block will be at some height h, so we can say that it has potential energy mgh. The block at the very end, when it reaches its highest point, there will be no movement of the block. The block will momentarily come to a halt. That means there's no kinetic energy, so that is 0. And we do have heat loss because for a distance here equal to 5 meters, the block has to travel across a surface with friction. So that means that this is plus the friction force times the distance traveled over the surface there. Now I have to be careful. I shouldn't use the same d here as I use here. That's a different distance. So let me just make it a big D to differentiate between this distance here and this distance here. So let's write it like that. Now, since the block is sliding over a horizontal surface where there's friction, the friction force is simply the normal force, which is equal to the weight of the block, times the coefficient of friction. So in this case, we can say that we have 1/2 kx squared. That's equal to mgh, the final potential energy, plus the weight of the block, which is the normal force of the surface pushing back. And just to make sure we understand here what we're doing, let me illustrate. So we have the weight of the block, mg, the normal force pushing back, the surface pushing back against the block, which on the horizontal surface is mg, the friction force, which is going to be directed in the position opposite from its motion. Since the block is traveling this way, the friction force will be this way. So force friction, which by definition is the normal force times mu, which is therefore equal to mg mu. And so that's what we have here. The friction force mg mu times the distance traveled over the surface. We need to do one more thing. We do not know what the height is. And we're not looking for the height, we're looking for distance traveled. So we have to convert from height to distance traveled. This is a triangle. Here we have the angle theta, which I believe I said was 30 degrees. Okay? And so the relationship between the hypotenuse, which is the distance traveled up the incline, and h, which is the opposite side to the angle, we can say that h, the opposite side of the angle, is equal to the hypotenuse d times the sine of theta. Or we can say that d is equal to h divided by the sine of theta. So instead of writing h here, I should write d sine theta. So one more conversion of the equation. We have 1/2 kx squared equals mg times d sine theta plus mg mu d. And the only thing we don't know here is this distance right here, the distance up the incline. So we now have to solve that equation for small d. Everything else should be known. K is known. The amount of distance the spring was compressed, the amount of distance that we travel over the rough surface. We know the mass, we know g, we know the angle, theta, we know mu. So now let's solve this equation for d, which means we're going to move this term to the other side. So now we have 1/2 kx squared, and this is that, minus mg mu d is equal to mg d sine theta, like so. And then if we divide both sides by the coefficients of d, the other terms here, or not the other terms, but the other components here making up this term, we divide both sides by mg sine of theta, mg sine of theta. We divide the right side by mg sine of theta. Notice that the mg cancels out, the sine of theta cancels out, and we're just left with d being equal to what we have on the left side of the equation. And then all we have to do now is just plug in what those values are. So this is equal to 1/2 k, which is 1200, x, which is, now be careful here, even though I said it's 50 centimeters, we have to convert to standard units, which is meters, and 50 centimeters is 1/2 meter. So 0.5 squared minus the mass, which is 20, times g, which is 9.8, times mu, which is 0.2, times the distance d here, which is 5 meters. The whole thing divided by the mass, 20, times g, 9.8, times the sine of 30 degrees. Now notice, I did not put in any units here. I did that in the interest of space. I'm kind of running out of space here on my board. But remember, if we use standard units, newtons per meter, meters, kilograms, meters per second squared, meters, kilograms, meters per second squared, and of course mu is unitless and the sine of 30 degrees is unitless, then we should end up with the distance in meters. All right, now we need a calculator. So I have one handy here, and let's see what that number is. How far up the incline did our block slide? So we start with 0.5 squared times 0.5 times 1200. Okay, that gives 150 for this, minus what's there. So minus 20 times 9.8 times 0.2 times 5. That's 196 equals. So we're left with minus 46. Now that's interesting. So this is a quantity here, like that's minus. Let's write that down. So coming up here, let me calculate that again. That would be 1200 divided by 8 That was 150. So we get 150 minus that quantity right there, which was 20 times 9.8 times 0.2 times 5, which is minus 196. A negative quantity. Now that means something. We'll see in just a moment what that means. We're going to divide that by 20 times 9.8 times the sine of 30, which is 0.5, which is divided by 98, which is equal to the distance traveled. So what do we get here? We get 150 minus 196 divided by 98, and we get a distance equal to minus 0.47 meters. So what does that mean? Well, my assumption was that the block will make it all the way across the rough surface, a distance of 5 meters with coefficient of frictions. I shouldn't call it K, I should call it mu. Coefficient of friction is mu, not K. And then go up the incline a ways, but it looks like it never made it to the incline. It looks like, since I have a negative answer, that the block stops somewhere before it reaches the end of the incline. So how do we adapt to that then? That means that we do not have this term right here. Doesn't reach any height. And the question then becomes, how far along the horizontal portion of the distance that it traveled will the block actually make it? So now we're going to have to regroup and solve the problem again, a second time, by saying we do not have an MGH term, and now we're just going to solve for D. So let me write that equation down. Okay, so with the MGH missing, the equation now will become 1/2 kx squared, which is the initial potential energy it has when we compress a spring, equals, on the other side, mg mu d, the amount of energy lost by overcoming friction. And it looks like all of the energy we stored in the spring will be lost by overcoming the friction. We just need to know what d is equal to. So solving that equation for d, I divide both sides by mg mu, and we turn the equation around. So we have d is equal to 1/2 kx squared divided by mg mu. And now we plug in the values of those. So we have 1/2 times 1200 times 0.5 squared. Remember, centimeters need to be converted to meters. Divided by the mass, 20 kilograms, times g, 9.8, times mu, 0.2. Again, if I use standard units, newtons per meter, meters, kilograms, meters per second squared, I will get distance in meters. So now we get, that's, if I remember right, that's 150 divided by 20, divided by 9.8, and divided by 0.2, and I get 3.83 meters, or 3.8 meters. So the true answer is, a little bit deceiving the way the question was asked, it doesn't make it up the incline. The block will actually stop before it reaches the incline after a travel distance of 3.8 meters. And that's how you do that problem. All right, let's do a few more examples.